Okay, I think it's time. Good morning, good afternoon. Welcome to Indoor Ag Science Café for the month of May. I really appreciate your time to join with us, to exchange information, learning something about the science behind the technology of indoor farming. So this project is funded by USDA NIFA for the group of scientists and engineers working for advancing indoor farming forward. So the members include Michigan State University, Ohio State University, Purdue University, and University of Arizona. I'm Cherry Kubota. I'm a professor at the Ohio State University. And today we have a new face, actually not new face for me. He's a graduate student in my lab, John Arlo, who is gonna co-moderate this cafe and then probably the future ones also. So John, wanna say a quick introduction about yourself?
Sure. Hi, so John Ertl. I've been one of Sherry's students for 4 years now. I got my master's in her lab and then now I've switched to a PhD working on the project with the OptimIA group. And so it's my pleasure to be here today and meet you all.
Okay, great. John, so you're gonna introduce the some of the schedule and then introduce the speaker, and all yours for now.
All right. Okay, well, good morning, everyone. Thank you for being here. Let's advance this slide here. All right, so we have a few announcements about the schedule for the cafe series. So today is Dr. Murat Kacira presenting. On June 7th, we'll have an indoor farming technology showcase. So stay tuned to that. In July, there won't be a cafe. And August and September are to be announced, but we are taking suggestions. So if you do have a suggestion, feel free to email Dr. Kubota at any time to voice your opinions on that. And we look forward to scheduling those soon and getting that information out to you. A very exciting offering as well is the first annual conference for the Ohio Controlled Environment Agriculture Center that's opening later this year. And we're going to have a meeting talking about the advancement of microbial technologies for controlled environment agriculture. That'll be on July 20th. We'll have registration coming out soon, but it will be in person and Zoom linked. And so we will be able to, everyone should be able to participate in that, should you be interested. And there will be a great selection of speakers and information shared at that meeting. So please stay tuned to that event.
Actually, registration's already open. So
registration's already open.
Yeah.
Okay, great. All right. There we go. Also want to bring your attention to a new initiative, which is the OptimIA University, where we'll be talking about the basic knowledge of indoor farming. And so if you visit the website in the top right corner, optimiauniversity.org, you'll get access to a lot of information and recorded lectures about everything from indoor farming background to environment, managing different crops and economics of indoor farming. So please visit that website and we'll be populating more lectures as time goes on. But this will be a really good source of information for everybody. And so I hope you check that out in the near future. As for today, we'll have Dr. Murat Kacira present. And so we're going to talk about his introduction to computational approach to optimize air distribution. And so Dr. Kacira, if you would like to share your screen, I'll turn it over to you. Thank you for being our speaker today.
Thank you, John. Can you see the screen?
Yes, we can.
All right, excellent. Thank you so much again for the introduction, and also thank you, Cherry. This is, I believe, my third time presenting in our indoor Ag Science Café series. It's always exciting, and I also would like to say hi to everyone joining, and thank you for your time and for your participation. So today I will be introducing you about the computational approach using computational fluid dynamics technique to optimize, evaluate airflow, air distribution systems, and hopefully with an objective to come up with improved design alternatives that are suited for both greenhouses as well as indoor vertical farming systems. I will share with you some of the trends in terms of CFD. I will refer CFD from now on to computational fluid dynamics, applied to controlled environment agriculture systems, and some of our previous work, both related to greenhouse systems as well as indoor vertical farming applications. And I will also talk about the structure of the CFD modeling and what is required to perform the CFD analyses. So what is computational fluid dynamics, the CFD? CFD is basically the branch of fluid dynamics, fluid mechanics, using numerical methods, for example, discretization methods, and using solvers and numerical parameters with some grid generation used, and also using data structures to solve, to analyze and solve problems that are dealing with the fluid flow. So in the process, the conservation of laws, including the conservation of mass through the continuity equation, is solved, as well as the conservation of momentum equation is solved, as well as the conservation of energy is considered as part of the computational fluid dynamics analyses. So where is CFD used today, or in the past? So CFD has been used in many fields, including aerospace applications, automotive applications, biomedical, chemical processing, heating, ventilation, and air conditioning applications, hydraulics, marine sciences, power generation systems, or other fields effectively to analyze the fluid flow, evaluate design scenarios, work with what-if scenarios to improve the design as well as the operations of these systems. So why do we want to use computational fluid dynamics? Well, it is really a sophisticated engineering tool to simulate and design systems instead of building and testing many design alternatives, because it can be time inefficient, or it could be really costly. It's a tedious work to perform the experiments, to go through various design options. And also CFD really provides high fidelity database for diagnosing the flow field. As you can see here, with experimental work, you really need to deploy many sensors and collect the data, analyze the data. If the experimentation is within a wind tunnel, for example, then you need to consider the scaling up of that experiment with the data collected to relate that to a larger scale and full-scale system and analyses. Also, simulation of fluid flow is really a complex phenomena, so requiring various criteria to be met and implemented for the analysis. There are environmental effects and factors that can interfere with the analyses. There are also hazardous conditions that may affect the experimental work, and also the overall physics that is involved. CFD also provides the opportunity to gain really knowledge and exploration of complex flow physics. So if you kind of rewind and go back into the history in terms of the applications of CFD within controlled environment agriculture, the earlier studies, I would say the pioneering studies, actually started back in 1989 with the evaluation of airflow and ventilation process around a single span greenhouse structure. And this was the pioneering work that you see on this slide from my colleagues, my mentors, Limi Okushima and Sadanori Sase and Nara back at that time. As you can see, the computational capabilities were really limited. It was only possible to analyze a small scale system within using a Cartesian coordinate, very simple geometries, not really perfect as you can see here in terms of the structure, to analyze the fluid flow. But as you can see, the result of the study was, even back then, was really accurate, just with the exception that, as you can see, with the return flow in the leeward side of the roof, close to the vent, as you can see, the wind tunnel study is showing some return flow versus the computational fluid dynamics is not actually able to capture that. I believe this might have been due to the limited ability in terms of creating a geometry and mesh that is really representative of the system that is being analyzed, also enabling an accurate representation of the fluid flow relative to the structure that is being evaluated. But still back then, with those computational capabilities, it's been a nice study. And following that work, later in the 1990s, we see further implementation of CFD to analyze greenhouse systems and ventilation and airflow. As you can see, comparing CFD models to wind tunnel generated work as the basis to validate the model first. And here with this work, the researchers have been evaluating different turbulence models applied to the analyses to see their accuracy and their use to analyze the airflow on a two-span greenhouse to analyze the ventilation, as you can see, using roof vent, continuous roof vents. And later, we started our earlier work with the CFD analysis applied to greenhouse systems. This was my work as part of my master thesis back at that time. As you can see, the computational capacity that we were using with the PCs in 100 megahertz with a limited computational cell capability to analyze the airflow around this Sawtooth greenhouse design to compare continuous roof vent basis designs versus roof vents also supported by side vents to improve the ventilation and air exchange within the greenhouse, as well as within crop canopies, without considering the crop and canopy existence in these models with earlier studies. And later on, our understanding of the CFD really was improved, and also the computational capabilities with the CFD programs were improved, allowing us to integrate crop presence or coupling physical as well as biotic processes using additional or extra additional functions called user-defined functions connected to main module or the model of computational fluid dynamics software to integrate crop presence or other biotic processes to represent the problem domain better and more relevant to the application. In this case, you can see early in 2000, this study incorporated crop canopy and crop presence, considering the plant canopy as a porous media in the analysis, as well as also looking into the spore distribution. Spore distribution is also a concern in controlled environment agriculture systems. So these researchers actually were incorporating a function that allowed them to analyze the spore distribution within a greenhouse system that you can see here on this slide. Later on, again, developing a better understanding of the CFD and including other biotic applications or abiotic coupling, abiotic transfers and plant activity. Researchers were looking into, for example, the transpiration process. As you can see, leaf temperature distribution in a canopy stand, as you can see here. Transpiration process within the plant canopy under a given environmental condition or the canopy structure in a greenhouse system, as well as the radiation distribution, solar radiation distribution inside the plant canopy, comparing the experimental measurements versus the computational fluid dynamics generated simulation results. And then, for example, carbon dioxide distribution in a greenhouse system was also evaluated and incorporated into the CFD applications in controlled environment agriculture systems. So later on, CFD really, the interest in CFD analyses grew significantly over the years, exponentially, I can say, and that the CFD analysis was implemented to natural ventilation analyses, mechanical ventilation, the effect of insect screens, crop transpiration effect, crop presence effect, because the crop presence creates a drag force against airflow, and also crop presence affects the transpiration process and heat exchange between canopy and the surrounding air, affecting the airflow as well, in addition to the environment. These were being incorporated into the analyses, the heating systems analyses, the effect of solar radiation, spore distribution, cooling systems, pesticide distribution, condensation, as well as alternative energy integrated greenhouse systems. You may find studies incorporating photovoltaic systems or covering materials incorporated into greenhouse systems and their effect in terms of the environment that is created under such structures or integrated structures in a greenhouse system. So here's an example CFD modeling structure for environmental uniformity analysis that we performed back in 2013 with one of my master's student, Ihab Tamimi, evaluating the effect of high pressure fogging system deployment on the side of the greenhouse at the gutter height level, as well as the deployment of the nozzles within the center of the greenhouse, injecting water into opposing directions to evaluate its effect in terms of the uniformity of the environment created, mainly analyzed by the vapor pressure deficit distribution within the greenhouse, particularly within the canopy zone that is represented by the rectangle that you would probably see with the faded black rectangular line there representing the plant canopy, as well as the effect of side vents and continuous roof vents in this greenhouse. So the CFD analysis starts with the definition, with the defining or creation of the geometry. We need to create a geometry that is representative of the problem and the problem domain. And then, since the computational fluid dynamics uses a finite volume method, we need to create a mesh. We need to divide this large volume problem domain into fine, discrete cells, so the conservation laws can be solved, the equations can be solved for continuity, for mass and momentum and energy within each cell, each volume, and the result being transferred from one cell to another to complete the overall analysis. So that mesh, the mesh quality is really critical in terms of the accuracy of the CFD analysis. There are techniques to do that. There are ways to check the quality of the mesh, so we can incorporate a good quality mesh into the analysis. Then there is the solver. the conservation equations that are being considered, a turbulence model incorporated to analyze the fluid flow. And then if we are incorporating, for example, the solar radiation effect in terms of the direction of or the positioning of the sun, for example, for the radiation or the transmittance of light transmission through the covering material. The cover material properties are being incorporated into the solar load model, and then the radiation model is also used or activated to evaluate or consider the radiation process from surfaces. For example, the cover material, the radiation from the surfaces or wall surfaces, ground surfaces into the problem domain. Then there is the crop presence. The crop presence can be or has been incorporated into CFD models using porous medium approach. In the porous medium approach, a block is generated, a representative zone is generated in the problem domain with a porous jump technique considered or domain defined, where the porosity of the canopy or the drag coefficient for the canopy is considered to integrate that effect of the crop against the fluid flow. And then in this particular analysis, with our greenhouse system evaluation with high pressure fogging, as well as our interest to see the distribution of vapor pressure deficit, to look into air temperature and relative humidity distribution, we needed to use the species transport model, which considers the mass fraction of the water in the environment. So that's how we are able to evaluate the relative humidity or the vapor pressure deficit distribution in the as a result of the CFD analysis. Then we also use a discrete phase model because of the high pressure fogging system injecting water droplets into the air. So the trajectory of the water droplets in this analysis was considered through the discrete phase model activation, so that we can track the travel of the droplets within that problem domain. And then since we are considering crop presence in the model, then we wanted to include transpiration as a user-defined function. This is something that does not exist in CFD softwares or tools that you have right now commercially available. This is something that a modeler needs to create the code and hook it or integrate it to the overall problem to the solver, so the transpiration can be incorporated, which in turn affects of course, the sensible heat, latent heat conversion, and then the effect around the temperature, around the plant canopy, as well as the mass fraction of the water and all that interaction between the canopy and the surrounding environment. And then results are, once the conversion is achieved, then the post-processing of the analysis of data is performed, where you can create graphs and figures like the one that you see on the slide with field contours, looking into the details of the variables of your interest. For example, temperature, maybe air current speed, vapor pressure deficit, carbon dioxide distribution. So whatever the interest that you have or you incorporate it into the model, you can look into these distributions or the uniformity, for example, in each coordinate in a detailed fashion. So that's the beauty of computational fluid dynamics. So for any computational fluid dynamics study, there is a need for model validation. So we have to make sure that we have a good model that is representative with an acceptable range of accuracies, so we can feel confident and then move to the next step, being maybe to evaluate various what-if scenarios or design applications or configurations. Related to the study that I showed you in the previous slides with the greenhouse case, Our model validation study included the radiation, validating the radiation model, as we created a small box covered with a polyethylene greenhouse cover with known specs in terms of the transmittivity, absorptivity, and all that information, including the temperature, air temperature measured, as well as the solar radiation measured within this transparent box, as well as the outside conditions were measured in terms of the solar radiation outside, the temperature, and we created the same domain, as you can see, this simple box in the CFD model, and we kind of evaluated the simulated temperature within different coordinates within the box, as well as those measured versus CFD generated results. In addition to that, as you can see, we also simulated the crop presence through with the air flow, the drag coefficients against the air flow, with the data that was available to us from a wind tunnel study. As you can see on the top, on the right top corner image here with field contours, and really repeating that, simulating that in the CFD environment to really feel confident that we were able to replicate that scenario, as well as generate the similar results in terms of the porous media approach that was going to be implemented in the model. In addition to this, we also had measurements for transpiration from an earlier study that was conducted. So we had measured values of transpiration in a given coordinate in the greenhouse, as well as comparing that to simulated values that we achieved from the computational fluid dynamics. So once the model is kind of validated, and then moving to the analysis of different scenarios, in this case for that particular study, as I mentioned, our interest was to really look into the deployment of the high pressure fogging system on the side of the greenhouse at the gutter level. The images on the left is showing that comparison versus the nozzle that is deployed at the center of the greenhouse at the gutter height, injecting water into two opposing directions for us to evaluate the vapor pressure deficit distribution in this greenhouse system. It was a three-dimensional study, as you can see on the top right corner of the image, but we are looking at the slices of the central slice presenting you the vapor pressure deficit distribution in this case. So the comparison was based on relative standard deviation of the vapor pressure deficit in 10,000 data points in this three-dimensional domain. So as you can see, the higher this lower this value, the better the result is. I believe in this case, the case number 9 and 15 were the ones that we identified as the best scenario in that particular design. As I mentioned, there is a possibility to use the user-defined functions, for example, to consider transpiration effect in the CFD model. This user-defined function inclusion in the CFD model follows these basically these steps. So the main steps include creating a file that contains the UDF source code. And then we can connect this to the solver and read into the case file and data files, and then we can interpret and compile the user-defined function to make sure that there's no error, there's no syntax error or other errors in terms of its compilation, and then we can assign the user-defined function to the appropriate variables and zones in the panel. And then we can set the user-defined function update frequency during the iterations. So the main module CFD code then can communicate with the user-defined function or the code iteratively during those iterative processes to generate the results from the user-defined function, and then consider that as input or boundary condition within each cell throughout the iteration process. So that's basically the structure of the user-defined function in CFD modeling. And I wanted to show you here in this example, in this slide, a model that would not consider user-defined function or the crop presence in the analysis versus including the crop presence, and see how that actually affects the result or the outcome. So you're looking at this top image where we did not include the user-defined function or crop inclusion for transpiration effect. And in the bottom, you can see the model was integrated with the user-defined function, and you can see how the result is affected or changed or improved with the crop being defined. And with the transpiration effect, you can see further cooling that is achieved because of the transpiration process, helping the environment, really to be cooled because of the transpiration process. And here's another example of with and without the UDF in the case of a central point installation of that high pressure fogging system. As you can see in the bottom, when we activated the UDF, you can see again the effect of crop transpiration and the cooling effect in that zone with vapor pressure deficit being lower compared to the case when you don't have the UDF incorporated in the model. So then we moved from greenhouse studies to vertical farm-based analyses. As you know, one of the bottlenecks of the indoor vertical farming system is the lack of uniform environment, a lack of airflow, uniform airflow, and the ability to actually move air around the plant or within the growing system or the facility. So we have been really putting a lot of emphasis into this work for the past 6-7 years, as we have been really seeing the need for airflow analysis. So in this case, one of my previous PhD student, Ying Zhang, did a research on incorporating localized air distribution system implementation in vertical farming system, so we can bring actually the conditioned air to each canopy layers within this three-dimensional production space. And our interest was particularly to prevent the tip burn issues that is really a main issue in the indoor vertical farming with lettuce crop. The ability of preventing tip burn in greenhouse systems with the use of vertical airflow fans has been demonstrated in terms of its effectiveness, and it's been implemented widely. However, incorporating that into vertical farming system under the constraints of the lack of headspace between the canopy and the LED lighting structures, light fixtures really demands for specific design considerations to really create a dynamic flow, a more dynamic flow to enhance the transpiration process, which in turn really improves the calcium uptake from the nutrient solution into the growing young shoot tips to prevent the tip burn. So with this work, we kind of aimed that objective. And then again, the CFD model incorporated first the geometry, generating the geometry, meshing that geometry, and then solving the conservation equations, turbulence model to consider the airflow. The energy model is activated to consider the energy exchange between the lighting system as well as through the walls and the canopy, and the species transport model is activated to consider the mass fraction of the water in the problem, as well as porous media approach to consider the crop presence in there with the drag against the airflow, and as well as the transpiration incorporated to incorporate that effect into the model. As you can see, in terms of the transpiration model, here is the general energy balance equation that is considered, which was incorporated into the user-defined function to consider the transpiration. So we're looking into the net radiation effect and the sensible heat exchange, and then the latent heat exchange incorporated in the energy balance in the user-defined function code, which is then connected to the main CFD model. So in each case, we calculated air temperature or the leaf temperature, and then the main code, CFD model incorporates that result as a boundary condition input variable in each iteration to continue solving the problem. As I mentioned, mesh quality is really critical for CFD simulations. We need to aim for a good quality mesh, hopefully finer grids and mesh generated around the area of interest, but in a way that the larger the number of cell size, then it would demand for the higher capacity is needed in terms of the computational capabilities. So it may take longer time for the convergence to be achieved. So there's kind of a balance that needs to be considered in terms of the number of cells and mesh size considered versus the accuracy that is targeted, as well as the computational time that is, or load and resources that are needed. So finer mesh are generated. As you can see here, we're considering different cases in this vertical farming system in terms of where the air comes into the facility and where it exits the vertical farming facility from ceiling on the sidewalls, or being brought in between the canopies or the multi-tier systems with fresh air, and then rejected or returned or exhausted from the ceiling into the air conditioning system. One other requirement is the mesh independence testing or study that needs to be conducted. As you can see here with the graphs, we are considering mesh independence test, which means that we start with a higher number of cell size or the mesh, a finer mesh, and then maybe bringing that down to a lower mesh numbers or the cell numbers to see if we are really able to achieve the same outcome or the accuracy that we are really wanting to see. So that allows us to kind of bring the need for the computational capability to a kind of lower level with an acceptable accuracy outcome from the CFD analysis. So this is really a kind of a requirement that I would recommend to include in the CFD analysis. So in the indoor vertical farming situation, as I mentioned, the non-uniformity of the airflow is a challenge. That also brings the issue with air temperature distribution, relative humidity, vapor pressure deficit, air current speeds that we would like to see at the optimal level, as well as the CO2 concentration distribution in the growing space. All of this is kind of really related to the plant growth, the photosynthesis and the transpiration process, and maybe leading to potential crop disorders, as I mentioned with the tip burn issue. So we need engineered HVAC system designs. So some of our earlier work incorporated these different kinds of airflow system. For example, in this case, you're looking at a multi-tier systems when the air is brought in from one side of the rack or the shelf, and then pushed out or circulated using these fans on the other end. As you may imagine, with the presence of the lighting system here and the air being brought in from one side and traveling through the canopy, the temperature distribution as well as the air velocity, air current speed distribution is not uniform in the horizontal as well as in the vertical domain of that system. So maybe the facilities that are using this type of air distribution system, especially with this transplant or production or propagate seedling production, this may maybe lead to non-uniformity in terms of the growth of those seedlings. So the growers, usually operators, have the need to turn their actually trays over that brings the need for extra labor. So an improved design is needed to optimize the airflow in this case. Earlier studies are showing that an air current speed of or between 0.3 up to 0.8 meters per second really enhances the net photosynthetic rate as well as the transpiration process for crops grown in controlled environment agriculture settings. So this was kind of a basis for us, for a criteria to incorporate into design analyses and air distribution system design alternatives in our CFD studies. As you can see here, the transpiration process is really affected by the boundary layer, how the boundary layer is formed, as well as the associated resistances against the water diffusion from the stomates into the air around the leaf and around the plant canopy. The driving force here is the vapor pressure deficit, as you can see, between the saturation vapor pressure deficit within the stomates, as well as the vapor pressure above the leaf surface. And again, in between, against that driving force or the flow of water, there are canopy resistances, particularly the aerodynamic resistance has an effect. So we need to really lower that boundary layer resistance or the aerodynamic resistance, as you can see, to allow the water to diffuse at an optimal level or improve the transpiration process. So the air velocity needs to be improved within the optimal range so we can lower or minimize the boundary layer thickness, as well as the aerodynamic resistance is also would be smaller, allowing us to create a better environment for the plants to transpire. So initially we focused on a single shelf to demonstrate some concepts around air tube or perforated air tube based systems to push air down into the canopy through vertical airflow. As you can see here, our study incorporated one perforated tube positioned between LED lighting system versus maybe two of them in an alternating mode positioned in the system. In one case, we are pushing air from one direction. In the other tube, the air is brought in from the other direction to see the effect, as well as 4 air tubes, again, positioned between the LED lights for us to see if we could achieve that air current speed optimal level that I mentioned on the canopy surface. So the images that you see on the right-hand side here is the top view of the air current speed distribution just on top of the canopy. So we were really looking into the range of air current speeds as well as the uniformity or the distribution of these air current speeds on top of the canopy surfaces. I believe this study showed that case number 2, in the case of this design here with 2 perforated air tubes with air in jets introduced into the canopy, as you can see in this image, from 3 different directions down into the canopy. Now we are looking at the side view of that plane above the plant canopy to bring the air on top of the canopy to create that dynamic airflow, enhancing the transpiration process. So from this work, and here's the temperature distribution, air temperature distribution in each case, as you can see, we're able to look into the details of the temperature distribution and also make a decision to improve maybe the designs in the analyses. From this work, this led to the following work where we considered really a warehouse-based system, in this case, a large warehouse with multi-tier system to evaluate various scenarios in terms of the inlets and exits for the air to circulate within the growing space. As you can see, our objective was to kind of compare this design alternative at the bottom that you see, where the air is being actually pushed into the canopy, into the multi-tier system to sweep the canopy surfaces with a horizontal airflow to improve the air distribution as well as the uniformity of the environment, and with the air being rejected or exiting from the ceiling. And of course, we included model validation study here as we deployed multitudes of sensors to measure air temperature as well as air current speed in our vertical farming facility here at the Controlled Environment Agriculture Center when the crop was growing in different layers of the growing shelves as well as within the chamber to collect that information and then create the same scenario and the problem domain in the CFD simulation to compare the measured values of air temperature and air current speed and compare that to the simulation generated CFD results. So the next couple of slides will kind of present the air uniformity, air velocity distribution, and air temperature distribution and uniformity under different design considerations from that study. As you can see, this is the case 0. Air comes in from one wall, and on the opposing wall, it leaves the structure. As you can see, this really does not provide a uniform air temperature and air velocity distribution in that vertical farming system. And here is the case with the inlets being on the ceiling as well as the exits being on the ceiling to push air down into the aisles. As you can see, again, the air velocity and temperature distribution is not optimal as we really would like to see in this three-dimensional domain. Here is another scenario where the air is brought in from the ceiling and leaving the facility from the side walls. As you can see, again, the distribution and the uniformity is not really optimized. And now we're considering some of the designs that we see also in commercial vertical farming operations, where there is a tube on the ceiling just above the aisles, pushing air down into the canopy, and then the exits also being on the ceiling on the other aisle. Again, the uniformity of the air distribution as well as the optimal ranges that we would like to see are not achieved in that scenario. So we've been encouraging a localized climate control with a proper ducting and design that would bring the air closer to the canopy, really where our main interest is with the crop to improve the uniformity of that environment and also to create the flow that we would like to see, enhancing transpiration, and also with the ability to inject CO2 or also to improve other environmental variables in the domain. As you can see, the vertical flow may not be really optimal in some of the designs because there's no standard design in vertical farms with the lack of head space. So that was one reason that we moved into this horizontal approach, horizontal airflow approach, sweeping the canopy surfaces in each layer. As you can see, these results were kind of showing some improvements in terms of the air velocity distribution that we would like to see, again, just above the canopy surface, as well as the air temperature distribution being more uniform when we compare this design alternative to the other design scenarios. And here's another study we performed with our Mars lunar greenhouse system. This is another indoor unique chamber that aims to demonstrate biogenerative life support system application for crop production, for edible food production, water harvesting from the air, as well as oxygen generation. Our earlier designs with this Mars lunar greenhouse system really incorporated an airflow unit that was short-circuiting, the inlets and exits being on one of the wall at the entrance of the chamber, with the air really short-circuiting with that design. So what we did was we incorporated that perforated air tube you can see on the lower left corner to bring the inlet air through that perforated tube, which you could also see in commercial greenhouses with semi-closed greenhouses, for example, to bring the conditioning from the below of the canopy and push it into the canopy to improve the uniformity of the environment. So that's what's been incorporated, allowing us to improve the air distribution in this particular design. So there are possibilities that CFD can really help as an engineering tool to have a good understanding of the problem domain and allow us to evaluate different scenarios. So as concluding remarks, I would like to say that CFD is an effective tool But I want to say it's a tool. So we really need to define what are the expectations and what are the requirements for our analyses. It can save cost, time to perform the analyses. Mesh quality is really critical for improved accuracy. Grid independence test is needed to improve accuracy and reduce the computational time. User-defined functions can be used to incorporate plant presence. There are some information available for the drag coefficient values for some of the crops that you can consider. Then the next step would be defining a reliable protocol to perform the CFD analyses and its validation, basically. For indoor vertical farming systems, I really believe that a localized air distribution system design can create an optimal growing environment for crops, and leaning towards a more or improved resource use efficiency, also production quality. So with that, I would like to stop here and then answer the questions you might have. I also included here some suggested reviews that you can consider in terms of the CFD analyses applied to controlled environment agriculture system. These are really great resources for those who are interested in the CFD analyses. With that, thank you so much.
All right. Well, thank you so much, Dr. Kacira, for this great presentation this morning.